I have more pictures of these kind of corridors, back rooms, the long, long paths where you look at it and you get scared, and how far is it going? So that's the kind of discussion on exams also, which never end, but we'll get to that. Today we have an interesting topic on nanobio interface, issues of nanobio interface. When we bring a hard, cold surface, think of it like a metal or semiconductor. So in every case, it's a hard, cold surface. And on the other side is the slimy, living things. Maybe we start with DNA molecule, simple molecule, or we go up in proteins, biomarkers, or even cells. So all those things are not hard. They consist of a lot of water and ions suspended in water. So there are issues at that interface that we need to know, and we need to, especially we need to know because the properties of those things are very different. If you look at a simple nanomaterial like carbon nanotube for that matter, which we have seen, there are many different issues. The energy on two sides is different. The mechanical properties are different. For example, for CNT, they have a very small curvature and very high surface to area ratio, which makes them very reactive. But on the nano side, you have on the bio side, you have molecules which have their own size, their own uh, reactive area, and we'll talk of some of those things today. Mechanically, one thing is very strong. On the other side, the bio side is very soft. The electronically, one thing has charges which are confined and settled in their spaces. On the bio side, charges can easily move around. If you look at the optical properties, we have very well-defined band gap in a semiconducting material, for example. But on the bio side, we have proteins, we have some fluorescent molecules which can, the fluorescence intensity can change very easily given the the change in ionic concentration, given there is a reaction, given there is a molecular binding. So a whole lot of things which are different. I've written magnetic. We will talk about magnetic today as well, which has to do a little bit about the dipole creation and movement of charges within a material. So all these things make it interesting for us to look a little bit deeper into the interface issues. And when we look at an interface and we really zoom in, we can model it in terms of how the ions are located and how they are moving, and how does the charge move in that at the interface. Hello. So here we are, yeah, there's a question. So here we are seeing there is on a metal electrode, there is a charge, right? So we provide it a charge, we negatively charge it or positively charge it. So that results into a potential accumulation on the hard side, on the nano side, the red thing that's shown here. So we say it's written charge induced on metal surface. So that results into a potential difference across the interface of two phases. And the most common is the accumulation of charge or transfer of charge across the boundary. But generally, yeah, on the nano to bio, there's the transfer is not as important, or as it's not so vivid in terms of the changes, more that there's redistribution of charges on the bio side. And that would be, and that's the reason in the creation of potential difference on the surface active groups. So that results into the ionization or induction of dipoles, or maybe the movement of charges. So here, as it is shown because of the negative charge on the surface. So water molecules are now accumulating close to right at the interface. So right, it's H2O. And that makes a kind of a shielding layer, a kind of a layer that would balance out the charge that's in on the nano side on the hard surface. So this electrical or compositional characteristics which come with the excess charge accumulation or excess charge density on either side, it redistributes what we would see or what we would think at larger scale. So hence we need to know what happens at the interface. So at the interface, we see something what we call a double layer. A double layer is where we have one layer which is right the opposite charge, which is called stern layer, like it's shown in the right-hand picture. And then on top of it, and stern is, as the word says, it's very tightly bound on the surface. It doesn't move too much. But on top of it, then there is a diffuse layer, which is less strict, but nevertheless, it still has higher density. So in this case, the surface is negatively charged, so it's the accumulation of positive charge on the other side. And zeta potential has a major, so we use zeta potential to quantify what would be the charge on a material. So zeta potential is a quantity for which tells us about the electrokinetic potential in the dispersion of a fluid. So in this case, we use the Greek word zeta to find out to describe zeta potential. And there are a bunch of things that go into that. The viscosity of the solution goes into that. The electrophoretic mobility, which means that how fast the ions can move into solution or into the hard surface. So it comes, when we talk about solutions, we talk about zeta potential. When we talk about surfaces, we talk about the what we call isoelectric point. So that's another quantity we'll talk about today. So if you think about even raw water, just water, that also has a zeta potential from -15 millivolt to -25. So this negative symbol tells us that the net charge on that object, whatever we are talking about, the water molecule, that charge is negative on it. And different materials have different isoelectric points. So now isoelectric points is something which has to do that what would be the pH at which that material will become neutral. And that also plays into the nanobiointerface, and we need to know what's happening when. So we need to know isoelectric point, we need to know what should be the pH we should be using, because that's going to result into the double layer formation. And that would result into the mobility of fluid, whether it's a nano channel or it's a micro channel. So at nanoscale, so there's a bunch of properties. Electroosmotic flow, we have seen this before. So now when the double layer happens, if the channel is large enough, we are not too bothered. But when the channel becomes too small, then the accumulation of charge would result into changes at the overall flow of solution through the channel, micro channel, nano channel. And so much so that simulation so that if we have a solution of, if it's in bulk, if it's 0.01 mole, now the concentration near the surface and middle of the channel would dramatically change. So this would be at close to the surface, the molarity would be 3.21 moles in this example, and in the middle would be 0.2 moles because of the charge from the surface of the material. So that gives us a kind of understanding that at the nanobiointerface, there is much more happening. Flow of solutions, again, because of the reduced drag and the electrophoresis and electroosmotic flow, which again, electrophoresis is the solid, where solid and liquid particles, they all move under the influence of electric field, and electron osmosis is where only particles can be separated in the external electric field. In blood proteins, in other bio things that flow, we can use electrophoresis to separate out those things based on their how much dipole they have. So now we talk about dipole. We know dipole moment in terms of capacitance, right? In terms of capacitors, but now we are talking the same thing for biomolecules. So think of it as electronic properties or electric properties of biomaterials or the biocide, which influences the design of our devices. So here I've just written isoelectric point for surfaces and material. For silicon dioxide, it's 2, for alumina it's 9. And we'll see what does it mean in terms of pH and the material. So charge at the interface, again, because of the charge, the zeta potential results into a specific charge accumulation, and that charge then can be neutralized by changing the pH. So it is the potential where the pH will be adjusted in a way that it would neutralize the charge from the surface. So we know pH. On one extreme, we have hydrogen ions. On the other extreme, we have hydroxyl ions, right? Plus ions and negative ions. So moving on the pH scale would result into excess of negative charge or excess of positive charge, hence neutralizing the effect of the surface. So, and that's a whole range for different materials. So we talk about isoelectric point in terms of the pH of the solution that would be required to neutralize it. And isoelectric points is for anything that contains charge, whether that's a surface, a hard surface, whether it's a protein. So even proteins have their own isoelectric point. For example, thrombin, BSA, human albumin, streptavidin. So these are the isoelectric points. Now, isoelectric point will tell us that what would be the movement of the material. So what would be the overall charge on that entity? And if we know what would be the charge, then we can easily find out if it's positively charged, this is going to travel to a negative electrode. If it is negatively, if it's positively, if it's negatively charged, it's going to go to positive electrode. So buffer, the solution in which an entity is floating, a particle, protein, DNA, even for that matter. So knowing that at that pH, what is the overall net charge will tell us which side is it going to go in a device, right? So the concept of isoelectric point is important to understand the nanobio interface issues. Now, when we now know the molecules have charge and they would be in a solution where their charge is prominent, now we can disturb with nano devices those charges that they carry with them. For example, in a nanopore, if you have a DNA molecule which has a potassium ions which are around the whole DNA, you have phosphate in the solution, you have, so this is the case of KCl. So where DNA is suspended or floating in KCl. So if you put it into a nano channel where we apply voltage across the channel, that voltage can strip the charges from single molecule. So we can perturb or we can shift those charges on biomolecule. Why is that important? That if you think about proteins, their folding or their whatever structure they have gives them the functional properties. So that, but that structure comes because of the ions that are distributed in neutral environment. If we disturb the ions, we'll be disturbing the structure. If we disturb the structure, we'll be changing its functional property. We'll be changing its binding affinity. So at the nanoscale, then we have to know what kind of forces we are applying and how are they going to impact ultimately the binding affinity, ultimately the recognition capability of those molecules. So a probe target interaction can dramatically change because of the charges. So here's an extreme example. If we apply too much field, that would completely transfer the shielding charge on a DNA molecule on one side than the other side, leaving one part of the DNA molecule devoid of any charges with it. So that is at nano scale, we can shift the charges dramatically. Now, if we can shift the charges, which means we can create dipoles in those. And creating dipoles is where we get to see dielectric properties of biomolecules. Now, we know dipoles and we know the capacitor, basic structure of capacitor, where we have two conductors and we have one insulator. And the insulator layer is the what we call dielectric. So the properties of dielectric are very important because that has to go under the transient dipole creation, hence the accumulation of charge on a capacitor, right? So we know basic capacitor. So here now we are talking about the dielectric properties of living things, of cells and bacteria. So what happens is when we put living things, the cells and bacteria into high electric field, we can change the permittivity. And if you think about permittivity, that's the physical quantity that tells us how electric charge can affect a medium, right? A material. How can it result into shifting of positive charges on one side and negative charges on one side? And that's what's called polarization. So the polarization occurs in response to the field. And that's when we do that, the polarization results into reduction of the effect of the actual voltage that's applied. So that entity that can polarize would get less effect of the voltage itself because in itself, it's going to readjust its charges. So the movement of that charge entity is going to become less because it has adjusted its charges. And that's the idea behind dielectrophoresis. We'll get to that. But here, just wanted to show that cells can undergo dramatic change in permittivity. And that results into a property that can be used to possibly separate out different entities that have different dielectric properties. For example, cancer cells and normal cells have different dielectric properties because cancer cell has larger water content, it has more negative charge on it. And we know these properties now. And using that, we can make two electrodes and we can possibly separate out normal cells from cancerous cells based on their change in permittivity, which would be different. So this graph, the x is in log scale, but this is going from kilohertz to megahertz, and that's showing how the dielectric or permittivity is changing for a cell. So that translates to what we call dielectrophoresis. So dielectrophoresis is, so when you have a potential applied on a fluid or bunch of cells, for example, or bacteria. So the internal shift would result into the overall movement of those living things up to a distance, depending on their polarization. So some would, so the idea is they're balancing out the uneven charge, right? So negative to positive electrode. And that polarization, the capability of polarization would result into some of those cells or bacterium to move certain distance than others. And that can be used to identify or separate out those things. So now every living thing, every biomolecule has either charged ion, which is part of its structure, or it contains those charges in itself. And that's something which can be used to possibly separate cells. And there's lots of work that has been done. So now when you then look at electrophoresis, we have a medium, we have a solution, and that has its own dielectric property, dielectric constant, and now you have a floating bead or floating cell or floating bacteria, which has its own dielectric constant. So if the dielectric constant of that entity, here it's given as polystyrene beads, EP, epsilon P. So if that's less than the material, it's going to have a negative DEP. A negative DEP would mean that it would travel away from the electrode. On the other hand, if it is have positive DEP, that's going to travel towards the electrode. And that's again a scale shown on the right hand side, that where the forces are changing as we move away from that electrode. And that can be used to, and it has been used to separate out particles based on their dielectric properties. So it's red versus blue is showing you the direction of. So the basic idea is that their dielectric constant would be used to separate them out in a given system, and that can be used for cell sorting. That can be used to sort living things, bacterium, based on their dielectric properties. So dielectrophoresis is the process which we use to do that. So now here we would need to know, we would have to know how much charge would be required, how much potential would be required to separate out one cell from the another type of cell. All right. So I can see some messages. My voice is cutting. Can everybody hear me okay?
Yes.
No, it's okay. It's okay, sir.
All right. Now, flow at nanoscale, we talked in previous lecture on the flow, but let's just recap a little bit. So solid to fluid, and then within fluid going to from large scale fluid to small scale fluid is a big difference. So now what happens is there's something else happens, which is that the selectivity of a solution can change based on how much is the flux, how fast do we move things. So if I have an electrode system or a nanopore or whatever interface we make, and we flow through things. If we flow them slow, we can have more effect and be able to separate out one thing from the another. So here it's shown a red thing is a cation and anion, positive ion and negative ion, and there's water. And it's just showing that we can be, if we flow things slowly, we can separate out those two from each other. But if we flow them too fast, we would lose selectivity. We can move things much faster. Permeability is faster, which means we can move things quickly, but we lose the selectivity. And we have seen that, and it's intuitive as well, that if you, for example, if you have a target molecule on the surface of maybe a flat surface or surface of nanopore, you have to move things fast. So you have to give time for the target molecule and core molecule to interact. If they interact, you can separate them out. But if you push them too fast, so now the fluid flow is not giving enough time for binding events to occur. And that can result into loss of selectivity. So you see this triangle, it's interesting how they made in this paper. I really like that. So what it is showing is we move too fast, we can get much more permeability, but we get the less selectivity on that side. All right.
Sir, इसकी measurement किस तरह करते हैं sir ये smart tools और?
Okay, so how do I find out selectivity? So we take the sample out and we look at the ionic concentration, and that tells us that if positive versus negative, how many ions have made it to the other side. So if you can dramatically increase one ion than the other, which means your pore has done selective transport. Or we take, if it's DNA, we take the DNA we take the sample and we run it through gel and see what are the sequences and what's the concentration of those sequences. There are tools, there are machines. We use UV-Vis, where we can look at the concentration of DNA molecule, how much made it to the other side. So if we sample at different time intervals, we can find the concentration change that we can compare for one flux or one fluid flow to the other fluid flow, and we can compare the overall result from that. All right, so again, this has to do with how much effect would we let the nano device or your nano channel take on the selectivity issue if it moves too fast or moves too slow. Another thing, now all this has to do with molecular recognition. If we talk about selectivity, so we are talking about molecular recognition. So now where a part comes where we need to know what are the energies involved when there is a recognition event occurring. Now, here is some data that we did some simulation a few years ago. So what we see here is if you move things too fast, we lose the hybridization rate. So hybridization rate becomes less. So if you see on x-axis, it is 1 over s, which is the reverse of the scale. But if we move things slow, we can have more hybridization. So in the upper picture, we are showing this circle to be the target molecule, and the black ones are the probe molecules. So if we have a target molecule coming through, if we move it too fast, it will not have time to interact with a probe molecule. Now here we are modeling probe molecule binding with target as a potential, the potential, electric potential. And this is, in reality, the binding is change in energy. And we have specific equations on how to model that. But if we move it too fast, it will just do what we call as tunneling in devices, right? So we know electronic devices, the concept of tunneling where a charge carrier can just zap through a barrier. So it's the same thing when we are modeling interaction of biomolecules. So their binding is an event that results into overall reduction and gives free energy. So it has to do with entropy and enthalpy. Basic physics concepts, the overall disorderliness. So when they bind, the overall disorderliness goes down, which what we call as reduction in free energy. And that energy translates to the potential of binding. And the literature has the exact numbers of those bindings and what is from any binding event, what is the overall change in free energy or the difference in potential between one kind of binding versus another kind of binding. And that's something which can be used to even detect or calculate the addition of good energy, reduction in energy, or bad energy, which is increase in energy from any mismatch. So here there are two sequences. One is shown as perfect complementary and probe molecule. And the lower one is showing one mismatch. So that one mismatch versus two mismatch versus three mismatch. There is a contribution of those mismatches. So that contribution is the positive energy, right? And that can be calculated and that can tell us how stable would be the molecular recognition. So, and there are, if you look up, there are websites where you can just lay out your sequences and can calculate those numbers for you. So here what we are looking as dG is the delta G. Delta G is the free energy. And it's a negative, which means the binding brings the energy down, right? But the overall change in the system from perfect complementary to mismatches, there is more contribution to the there is less contribution to the free energy when we go down. So it's in negative, right? So the smaller number is, so we go up, increase, we go down, which is smaller. But that the contribution results into what we call as change from in the TM. So on the right-hand side, you see the word TM. So TM is melting temperature. Melting temperature, we saw that before, is the temperature at which double-strand DNA turns into two single-strand molecules. So which means if there is mismatch, that can happen at less than room temperature. But if it is a perfect complementary, that binding and stay stable up to 35 degrees. So we play with these sequences because they would then tell us that how stable would be the molecular recognition in a probe and a target molecule. We can also measure the actual molecule's dimensions, because when we are dealing with nanoscale devices, we need to know what should be the size of your molecule. Apart from the binding affinity or the sequence that binds, sometimes we put spacer molecules just because we want to cover the whole surface or cover the whole radius of a device. For example, if we have a nanopore, so we calculate the exact size of a molecule using simple calculation, simple geometry. So we know base to base distance, right? And now if you have a linear sequence, you can just use that number. But if you have a sequence which turns into a loop, you can just model it as a circle. And you can find uh, the, the diameter, and that can tell you what would be the contribution of that loopy part into those calculations. So that will then go into defining the molecular recognition of a device. For example, in this case, if there is a narrow channel, so the left side is just showing the channel from a side, the right side is showing the side, a cross section of the channel. So we are taking that the centermost part, which says 20 nanometer, and we are looking from the top on the left hand side. So if you were to create a self-assembled monolayer, I'm happy with the homework you guys have submitted. So you know self-assembled monolayer. So if you are creating a SAM, we know the thickness of SAM. So that will have to translate into what is the size of your nano device and what kind of thickness do you need to create to maybe cover the whole opening so no probe molecule goes through without binding, right? So now how do we model this? Just take a simple term where you can model it as a cylinder, right? So these are approximations, but the data of the actual dimension can easily be translated into a range of your calculations. For example, if you are talking about a, a nanopore or a flat surface, so that would differ on how your molecule is modeled there. So on a surface, it would be covering the whole sequence, and then you can model how close a molecule will come from each other. And there are different things that go into, for example, if you're talking about a DNA molecule, then there's, we have a thing called radius of gyration, that if it is standing, how far can it just go around? So sometimes you want to put them very compact, sometimes you want to make them less compact. So defining your SAM is not a fluke. We actually calculate on how much concentration of the solution we would make to get what kind of compactness on a surface. In case of comparison, we can always, if you have a cylinder, we can open it up and treat it as a sheet, and then transfer it into the cylinder and see how the molecule spacing changes, the compactness changes. So these numbers are there in literature where the binding energies are already calculated, melting temperature already calculated. So here's a simple example of finding the binding affinity between a single target molecule. So if you have a cylindrical thing and we say, okay, if I have one target molecule, what is the affinity or what is the probability of binding? So we can start with simple concentrations. And we say, okay, there is a probe, there is a target, they have their own concentration. So this big bracket, we use that for concentration. So simple equation, one probe, one target would result into one binding of one probe and one target, right? So we start with that and we say, okay, if there is just one target, how is that going to affect your binding? So we use mass balance equation where we say that the binding is equal to how many targets are there. It's not dependent on how many probe molecules are there, because we have plenty of probe, but only one target molecule. So that becomes equation 2. And then we say, okay, overall, the probe change is that there's all the probes, and then there is one molecule which is bound with the target, and that becomes equation 3, right? So from there, we can then find the binding affinity, which is just the concentration of the probe divided by concentration of target at the start, right? So we have to go through simple manipulations to find out what would be the binding affinity of those things. And that can result into the design of your concentration, design of your SAM, and how would you, what kind of interaction would you expect from there? So here then we can plug in the cylinder properties and we can find out uh, in one cylinder what is the probability of binding. So a little bit more uh, intensive calculations, but the idea is that we can then take those numbers and find the area, and then from the concentration of the molecule in a solution or concentration of the probe on a surface, we can find out how many molecules would be there and what kind of liquid or what kind of solution would be there that can give you that the binding or that detection that you are looking for, right? So here we have calculated that 1 femtomolar in 1 microliter would have this many molecules, and that can then tell you what kind of SAM do you need to capture those molecules in that solution. So the size of the nanopore would have a, or the size of your nano device for that matter, will have a direct influence on the selectivity and the permeability of the solution and resulting binding with your molecule and resulting detection of your or your device, right? So these are few things that we have to know when we talk about nanobio interface. So when we talk about designing a device where we have to interface the cold hard surface on the nano side with warm slimy solution of the bio world. So, all right.